Okay, so what I'd like to do next is prove Minkowski's inequality, and so remember what that is. If F and G are an LP of E, then a triangle inequality is true. So we did prove this for P equals infinity in the last video. So we'll focus on P between 1 and infinity. Okay. The key tool is something called Young's inequality. Okay. And what is that? So if P is between the one thing I should say, this is pretty trivial if P is equal to 1, just using a triangle, inequality. So I will focus on P strictly between 1 and infinity. Okay. So if we define what's called the conjugate exponent, I really don't know why or where the term conjugate comes from. Sometimes it's called the dual exponent. For reasons we will maybe discuss in another video, maybe this video, I forget which. But let's say this is P over P minus 1. One of the key properties, and actually it's equivalent to cubing P over P minus 1, is that 1 over P plus 1 over Q is 1 over P plus P minus 1 over P. Well, that's just P over P is 1. Okay, so the claim is for any non-negative x and y, or sorry, a and b. We have a b is a to the p over p. Sorry, it's less than or equal to, obviously not equal to, plus b to the p over, b to the q over q. Okay. Yeah, so what we're going to do next is prove this. And it's an easy consequence of convexity. Let's say f of x is e to the x. So this, of course, is e to the x. It is bigger than 0 for all real numbers. And so that means this is convex on R. So what does that mean? If I have, I'll draw a picture to explain this if you haven't seen convexity before. So strictly speaking, convexity is the following. Yeah, and I'll just draw the picture before I even explain what this means. Okay, so I'll go back to what this means in a second. So the picture is as follows. We draw e to the x, something like that. All right, so for graphical purposes, I will pick, let's say, a u here and a v here. Okay, so I have my points roughly here. Okay, so I have f of my 2 points here. Okay, so this here represents something in the line segment between u and v. And as lambda varies between 0 and 1, we have everything in the line segment between u and v. So let's say this is, say, right here, lambda u plus 1 minus lambda v. Okay. Okay, so this point here, you can check. Well, this is the x value, of course. Yeah, this is going to be a little hard to fit. So here's what I'll do. The x value here is this right here. And you can check that the y value of this point here is just simply lambda f of u plus 1 minus lambda f of v. Okay. Basically, going back to Calc 3, this is the point on the line segment containing these 2 points in the xy plane, corresponding to this x value. Yeah, this red line here is the line segment containing these 2 points. On the other hand, let's do a different color. This point here, same x value, but the y value, to put it here, is, well, f of this x value. Okay, so basically this is saying line set, so it's this is literally saying convexity, that the line segment containing these 2 points here sits above the actual graph. That's exactly what convexity says. It's this line segment here sits above this graph here. Okay? And this, the y value for this blue point is exactly this here. So, okay, maybe let me do this. So this is blue, so maybe I should use blue for this one. Good. Second. So I just circled is a y value for this point. And the definition says this is bigger or equal to the green y value, which is right here. Okay. This right here is this y value. This right here has y value, this one here. Okay. So yeah, that's what convexity says. All right, so yeah, so let's use convexity in a useful way. This is trivially e to the ln of a plus ln of b. This is equal to e to the 1 over p ln of a. And we have to multiply and divide by p and q so that I'll do purple. I get if this is lambda, then this is going to be 1 minus lambda. So this is lambda u, if I set this to be u, plus 1 minus lambda v. Okay. So convexity says this is less than or equal to lambda f of u plus 1 minus lambda. Just going back to here, 1 minus lambda f of v. F of v is e to q b. So that's equal to 1 over p a to the p plus 1 over q b to the q. And I should say that it's a pretty good Taylor series exercise to show that if the second derivative is positive, bigger or equal to 0 even on an interval, then f is convex on that interval in this sense. This Taylor's theorem. Okay, so with Young's inequality proved, we're going to next need Holder's inequality. And one thing I want to make clear is that if p equals 1, then this is 1 over infinity. And it's still useful to think of q as infinity if p equals 1. Okay. So the next thing is something you'll use a gazillion times if you are doing analysis research. And it's the same Holder from Jordan-Holder Jordan-Holder theorem and group theory. So what's the Holder's inequality? Let's say p be between 1, and it could be infinity. So one thing also, so if if p is infinity, it kind of makes sense to think of q as 1. In particular, we always want conjugate exponents to be equal to 1 here. 1 over p plus 1 over q is 1 rather. So if p is 1, q has to be infinity. If p is infinity, q has to be 1 for this to equal 1. So it kind of makes sense. When p is infinity, we think of q as being 1. So let's say f is an LP of E. G is an LQ of E. E is, of course, measurable. Then the claim is this here is less than or equal to the LP norm of F times the LQ norm G all over E. Okay, so most people will say, without loss of generality, we can assume the norm of F and the norm of G are both 1. So let me basically essentially do that. So first, let's just notice that this is trivial when P or Q are, sorry, when P is 1 or when P is infinity, because, well, both of these are true. So almost everywhere on E. And same thing for G. All right, so in this integral, if Q is infinity, so P is 1, we can just pull out G and replace it with the L infinity norm of G. Same thing if if P is 1, then we just pull out, sorry, if P equals 1, then Q is infinity, so we pull out the L infinity norm of G here. If P is infinity, then Q is 1, so we pull out the L infinity norm of F here because we have these two facts. Right. So P equals 1 and P equals infinity is kind of the trivial case. So now let's get to the interesting situation where P is between 1 and infinity. All right, so let me set F tilde to be F over the LP norm of F, and G tilde to be G over the LP norm of G. Well, I'm going to assume both of these are positive. Sorry, it should be LQ. Yeah, this is fine because if either F or G are 0 almost everywhere, then that's equivalent to saying the norms are 0. So, basically, if either of those are true, the norm of F is 0 or the norm of G is 0, then F or G is 0 almost everywhere. So everything is 0. This integral is 0. The right-hand side is 0. So I can assume both of these are positive. Otherwise, everything is 0, not very interesting. So, right. So this means that the just by pulling out norms here, or by pulling out the LP norm of F, this is going to be same thing as this, which is 1. Right. Right. So if you have any doubts, just check it. Yeah, so the clever thing is, and what most authors mean by without loss of generality, assume the norm of F is the norm of G is 1. We're really going to basically work with these functions here, technically equivalent classes of functions, but whatever. Or I guess in this case, we are looking at functions here. We're going to look at these functions, F tilde and G tilde, that have both norm 1. Okay, yeah, so let's apply Young's inequality. Right. So technically, this holds for almost every x because we're assuming F is an LP, G is an LQ, so F and G are finite almost everywhere. It's fine. Yeah, so this is less than or equal to still tildes, so P over P. Here it's Q over Q. So just integrate both sides. I mean, yeah, like I said, technically, this is true almost everywhere. So what does this mean? This means that this is less than or equal to 1 over P times this here. Plus 1 over Q times this integral here. But what is this? This is kind of trivially, as I mentioned before, LP norm of F tilde to the P. What is this here? Same thing for G tilde, but this is 1 and this is 1. So this is just going to be, well, this is 1, this is 1. So everything is 1. So what do we have? We have this integral here is, this integral here is less than or equal to 1. That's what we have. Okay, so if you think about it, we're done. Why? Right, so I'm going to write it like this. And this is clever. I mean, this is pretty clever, this argument here. That's fine. Usually inequalities and things named after people don't have trivial proofs. Okay, so this is going to be equal to F over the norm of F times G, absolute value over the norm of G. And this is equal to, well, absolute value of F tilde G tilde, which is less than or equal to 1. So this is less than or equal to 1. So I'm genuinely done here. Oops. Sorry. Because I can just multiply by the norm of LP norm of F, LP norm of G. So LQ norm of G. Neither of them are 0, so that's fine. So that means, so really, really, really clever application of Young's inequality. Again, all I'm doing is multiplying by the LP norm of F and the LQ norm of G. Okay, so what I want to do next is just finish up the proof of Minkowski's inequality. And it's going to be a corollary of Holder's inequality. All right, so proof of Minkowski's inequality. So without loss of generality, assume this is not equal to 0. Right. Right, I mean, if this equals 0, then there's nothing to prove. What are we trying to prove here? I'm trying to prove this is true, so if this equals 0 right here, what I'm circling equals 0, then 0 is less than or equal to anything non-negative. So, kind of trivial assumption, but quite useful. Okay, so, right. And remember, I'm assuming, well, I'm assuming P is between 1 and infinity, but really I want to assume P is strictly between 1 and infinity because the case P equals 1 is really trivial. Just triangle inequality for complex numbers, basically. So yeah, you can do the case P equals 1. It's really trivial. So I'm going to assume P is between 1 and infinity strictly. All right. Right. All right, so it's easier to look at this quantity here, raise it to the P, than it is just to look at the LP norm of F plus G. Okay. Now, one strategy you might think to do, somehow cleverly use Holder's inequality, with my first function being absolute value of F plus G, and my second function being absolute value of F plus G to the P minus 1, and this is not a bad idea, it just doesn't work. You do Holder's inequality, you're going to basically essentially prove nothing. So we're going to do a kind of trivial thing, but it's really exactly what's needed. And that is this whole thing here is obviously less than or equal to absolute value of F plus absolute value of G. So this is less than or equal to absolute value of F. And now using Holder's inequality twice is going to do the trick. Okay. Right. So what I want to do, what I want to do is the following. All right. I want to use Holder's inequality with P here and Q here. Okay. So in particular, I want to look at Q. So let me write it like this. This one. So this is going to be multiply this by raise to the Q exponent. 1 over Q. It's a weird looking E. All right, so the question is, what is this? Well, we can figure that out very easily. Oops, do that. So remember what Q is. It's literally P over P minus 1. Maybe you forget like what it is. You do want to remember 1 over P plus 1 over Q is 1, and then you can just solve for Q. So 1 over Q is 1 minus 1 over P, which is P minus 1 over P. So Q is P over P minus 1. So you can always just solve for Q if you forget exactly what it is, assuming you remember this basic property here. This is really easy to remember. Okay. Wait. So this equals P, these cancel. P minus 1 and P minus 1's cancel. All right, so what is this equal to? This just becomes P. So this is the 1 over Q. And you can always think of this as green, I guess. Right. So you can always think of this as 1 over what I want to do. So I can think of this as 1 over Q, 1 over P, and then put a P here. That just has the effect of really just doing nothing. But this is the LP norm of F plus G, so this is going to be equal to, so a very useful little calculation. So it's the P over Q. Okay, so let's put this to good use. So strictly just use Holder's inequality. This is LP F plus G LP, and just hope things work, and they do work. Same thing, exact same thing. LP norm of G, LP norm of F plus G to the P over Q. Running out of room here. So what I'm going to do is factor this out, this common term here from both sides. Yeah, this is a really, really nice, clever proof. You do things kind of like this a lot in partial differential equation theory. So the idea is that we're going to take the quantity we basically want, modify it a little bit, raising it to the P, is less than or equal to something times the quantity we want. Again, modify it a little bit, and then solve for the quantity we want and hope that works. So I don't know directly how to just literally get this here is less than or equal to, I don't know how to directly prove Minkowski's inequality without this clever kind of argument. I'd be curious if you can avoid this kind of argument. I don't see why you would want to, because I particularly think it's a really nice argument, but yeah, so what am I talking about? I'm saying so this is less than or equal to this here. Okay. So what I need to estimate, what I want to estimate to the P is less than or equal to this times what I want to estimate to the P over Q. Okay. So I can divide by this because it is not equal to 0. We assumed this is not 0. So I can divide by it. And that just subtracts a p over q from the exponent of p here. Okay, so this means that so it's p minus p over q is less than or equal to this here. It's exactly what we want. So this exponent on the left looks a little funky, so you might be a little suspicious. But everything turns out fine. And as you would want. So hopefully this exponent here is 1. It better be 1 or we're in trouble. And it is. Because what is this? P minus p over q is going to be p 1 minus 1 over q. And remember, 1 over p is 1, so 1 minus 1 over q is 1 over p. So just solve for 1 over q. Sorry, solve for 1 minus 1 over q, it's 1 over p, so this is just 1. So this equals 1. So yeah, we're done. So yeah, that takes care of the proof. And I guess I'll just be clear. Yeah, it might be hard to appreciate. I mean, you really can't appreciate the utility here of Minkowski's inequality. I would say it's more advanced analysis. So on functional analysis, you really need a norm. But I mean, if you do data science, you do things in norm spaces, and you probably appreciate how useful a norm is. I'll say one more thing after this. So the conclusion is exactly what I want. Okay. So one thing to note, L2 is an inner product space, a complex inner product space. Yeah, and if you've done data, if you do any data science, you know that you're always happy when you have an inner product, because inner products are just so nice. There's just so many. And also, this is complete. I'll talk about that in another video. So what's the inner product? What kind of has to be true was F times G bar. Okay. So yeah, in another video, if you heard of completeness, completeness just means Cauchy sequences converge in your norm space. LP for P between 1 and infinity, including 1 and infinity, is complete. That'll be done in another video. That's a little technical, but nice, really nice proof. So in particular, this is a Hilbert space. Yeah, if you've done data science, you've probably heard of Hilbert spaces. Basically, they're inner product spaces where a lot of the algorithms you can come up with that you would assume should converge actually do converge. You kind of run into problems if you don't have a Hilbert space. I mean, that's not really quite true, because what you usually do, particularly for something like kernel ridge regression, you literally just force it to be a Hilbert space. So you complete it. but that's more advanced stuff. All right, so long, take care, almost done.